as we go through tonight's program, which should be about 45 minutes, we'll discuss the definitions, the standards briefly. We'll look at quality control. We'll look at the types of admixture. We won't focus on all of them. There are too many to do in one night. We'll look at the importance of doing trial mixes and, of course, dosing and the effects of using the right dosage. So let's think about admixtures to start with. Many people blame admixtures, don't they, when things go wrong? It's always the admixture's fault, as the joke says. But actually, in reality, admixtures are used in a very small dosage, less than 5% often, even down to 0.5%. But what they do is allow us to modify the concrete to get better performance, to get different performance, to enhance the quality and the performance of the concrete in some way. That's one way to use. The other way to use is to make things cheaper. So we can save cement. We can increase the speed of pouring. We can do a lot of things that we couldn't do if we don't use admixture. So although very small in their actual percentage usage, admixtures are a critical part of modern day concrete. So using them correctly is very important. So let's now think about the types of admixture that there are. You will hear about two different types: chemical admixtures and mineral admixtures. Chemical admixtures, as we said, are added, generally speaking, less than 5%. They're normally liquids, but not always. And they are used to save cement or reduce cost or enhance the performance. Mineral admixtures tend to be also sometimes referred to as additives, tend to be powders like fly ash, microsilica, GGBS, and they're usually used to replace cement or to improve the quality or the durability of the concrete. Now, today, given our time, we're just going to focus on the chemical admixture side. So in the standards, which we're going to just briefly touch on, there are two main ones that we should be aware of. ASTM C494 is the American standard, and there it lists 1, 2, 3, 4, 5, about 9 different types of admixtures by type. The latest one to be added is type S, which is very flexible for specific admixtures to give specific performance, as an example, to extend the slump retention or to allow us to produce SCC. But the others are fairly standard admixtures that are within the range: accelerators, retarders, plasticizers, and so on. If we look then to the European standard, EN 934 Part 2, also has the same type of products, but this time listed by actual type. So in this case, water retaining, air-entraining, very specific types, but the same list overall. Now what we'll do is pull out a few of those and we'll have a look at them in a bit of detail. So let's think about the basic admixture that everybody knows, and that would be according to the usage that we have. Now, if you look at that chart there, you see that by a long, long way, superplasticizers are the most commonly used product of the range. We have some plasticizers, we have waterproofing, accelerators, retarders, and so on, but they don't even make a quarter of the pie. Superplasticizers are globally used to a much higher extent than any other product. But let's just focus on the basic product, plasticizers, and we'll build up. So what is a plasticizer? Well, if you look at the EN standard, and most local standards refer to either EN or ASTM, so they're all linked. We're talking about very basic plasticizers that give between 8, 10, 15% maximum water reduction. Usually they're mixed in with the mixing water, and they're used to increase the slump. That's the main use of them. They're not so good at reducing the cement, so they're used to increase the slump of the concrete. They're very basic lignosulfonate based products or gluconate based products, and they tend to be from the 1930s, and so very, very old technology. So there you see the types of concretes that you can produce with them: quite high water cement ratios, medium slumps, not so high, very low grades, C10 to C30 typically, and dosage around 0.4 to 1%. We'll talk about dosage a bit more towards the end. Now, the nice thing about these is they're very cheap and they're compatible with all the other cement types, including your cement with fly ash, your GGBS and microsilica cements. So they're very friendly to use, but their performance is very limited. Now, if we go then to superplasticizers, which are the most common, they're the thing that most ready mix use every day and most precast are using every day. Let's think about there. If you think about the history of buildings, and there you see a chart of some of the world's tallest buildings, the trend is that it's increasing. Now they're building a tower in Jeddah, in Saudi Arabia, that's going to be even higher, 1,000 meters high, 1 kilometer high. So the demands on concrete are getting more and more and more, and so we have to produce admixtures that enable us to do that. So when we think about producing concrete to that standard, to be able to pump concrete vertically 1 kilometer, or to pump it long distance, or to pump it through heavily reinforced structures, then we need special concretes that are adapted. They're optimized for this type of application. So superplasticizers are where this range fits. Plasticizer would not be suitable for this on its own. So historically, from 1940s, 50s, we've had melamine, which has been phased out now because it was quite expensive and very short slump life. We still have naphthalene. You can still do that, use that. But more recently, we have the PCE type of admixture. You'll hear this term PCE. It's polycarboxylic ether admixtures. And they've taken over in the last 20 to 30 years of the admixture of choice. Now, why is that? Well, first of all, for the end user, they can give water reduction between 20 and 50%, which is huge. They blow away any of the other superplasticizers. Now, of course, that depends on the application. You don't need 50% for ready mix, but you might for precast. And there's where the other trick is, that the PCE molecules are easy to modify, easy to adapt. And so we can make many different types of concrete admixture from a similar polymer. So we have set retarding or high range water reducers, which would be used in ready mix. And we have set accelerating or straight water reducers, which are used in precast. And these are very, very powerful admixtures that need to be treated with care. You see from the performance range, the water cement ratio is much, much lower. It's down to 0.3, even below 0.3 with the right design. The slumps can be 220, 230, 240, self-compacting, 600, 700 plus flow. So very, very powerful. And the grades of concrete, well, now we're using them to make C150 ultra high performance concrete. So this is really why these PCE molecules that you'll hear all the admixture companies talking about are the future of where admixtures are going to go. Let's just briefly stop there, because they're the main types that everybody's familiar with. And let's just think about the pros and the cons of each type, because there are many. So if we think about the plasticizers, very basic materials, they are limited in what they can do. In terms of the amount of water you can reduce from the concrete, it's limited to 10 to 15% maximum. Here's where we start to talk about dosing. With some of the lignosulfonates, they contain sugar if they're not refined well. So if you use a high dosage, you can introduce retardation of your concrete, which means it doesn't set or can take a long time to set. So we need to be very careful on using them at high dosages. And it's old technology. For the naphthalenes and the melamines, again, you can have retardation if you use a very high dose. It's old technology, and to a certain degree, availability of these materials is can be a challenge in certain parts of the world. Now look at the pros. We did the cons, now do the pros. Lignosulfonate is cheap. It comes from trees. It's very cheap, and it's easy to use. So if you're in a situation where you're producing a low-grade concrete, say a blinding concrete, then you just need to use something simple like this. The naphthalenes, they're easy to use also. They're very friendly to cement. The cement can change the chemistry, but the product will be fairly stable. And we can modify the performance of those relatively simply. So there are some good advantages of those ones. If you then talk about the PCEs and the higher range, the very high range, they are more sensitive to the cement chemistry. And this is why sometimes admixtures can be working fine one day, and then the next day a new batch of cement comes and the performance is different. It's not that the admixture doesn't work, it's just the cement chemistry has changed and the interaction between the two is different. So we need to be careful of that. They are also sensitive to sand impurities. If you're in a country where there's a lot of fines or silt or clay in your sand, then you do have to be careful. There are now products around that are clay blockers effectively. They restrict the effect of the clay to allow the plasticizers to work better. And the one that everybody talks about is the cost per litre. Now, admixture companies don't like talking about cost per litre because the reality is it doesn't really matter. You can pay more per litre, but your cost per cubic meter can be less because you optimize the mix in various ways, reducing cement, reducing sand, whatever it may be, and to get a lower cost in use. This is what the admixture people like to talk about. And certainly as MC, that's the way we like to deal with it when we're talking about mix optimization. The plus points on the PCEs, they have a very high level of performance, as we said, up to 50% water reduction. The cost per use that I just mentioned is normally positive. And here's an interesting thing now, that the production of the PCE is factory controlled. The PCEs are cooked in a reactor for a set time with a set parameters. And so each batch is very, very controlled. So there's not much variation between batch to batch in admixture production. So that gives the admixture companies confidence that what they're producing is going to be suitable for the market and reliable. Good. So let's think that's covering plasticizers. Now let's, for a few minutes, just think about some of the other types of admixture. We won't go through all of them, but this will just show you some of them. So the ones that we know about regularly: retarders, accelerators, air-entrainers, maybe, depending on where you are in the world, durability enhancers, shrinkage reducers, corrosion inhibitors. You can see the list there. We will just pick out 2 or 3 of those tonight because we could spend a week talking about all these different types. What I would say is if there is any there that's particularly of interest to you, then talk to your local MC guys. They can help you with all of these different product types. Unfortunately, we don't have time to go through them tonight, but if you talk to MC, they'll certainly spend some time with you and help you to understand how each one of these work. So we'll just pick out a few to go through tonight. Let's think about retarders. Now, retarders. There is some confusion with retarders. People assume you can use retarders for extending slump life. We just add some retarder and the slump will last longer. Well, it's true, but it's not the primary reason to use a retarder. As it says on the first line in that slide, retarders are admixtures which delay or suspend the setting of the concrete. I'll show you that on a graph in a minute. But it has the side effect of also then, if the concrete doesn't stiffen, the slump stays for a bit longer. But it's not the primary way that they work. Because we delay the set, we slow down the hydration. The temperature comes down. So often we use retarders in mass concrete to lower the temperature. And we see a later increase in 28-day strength slightly. So where we would use them, high temperature concreting, where we need some extra life, mass concrete, prevention of construction joints. So we retard a section until the next batch comes in and then we merge them together if we need to. We use them in semi-dry concrete, which we can talk about later. Some formulations where you need long workability can be used with this in combination with a superplasticizer. And as I say at the end there, extended slump life. Now, let me clarify this. Retardation is talking about deliberately slowing down the hydration of the cement, delaying the setting. Slump retention is different. Slump retention focuses on maintaining the workability, the slump, as we call it, for a longer period. And often we use that through superplasticizers. It's true there is some overlap between the two. Retarders do help to extend the flow, but the goal of both is different. So sometimes when we think I can add a retarder, it would be better to use a superplasticizer. And so if you're not sure, just ask MC or the local rep that you're dealing with, Richard or whoever it may be, and they can guide you on whether superplasticizer is the right solution or retarder. So in the MC range, there's quite a few retarders around the world. There's two in Ghana. That's the 361 and the 370. Often they're the same role to delay the setting. The one you see in the picture is from Vietnam, actually, but they're often a different base chemical, so they work slightly differently. If you look at it on a graph, so the blue line, the purple line is our reference mix. It's our normal. Let me just see if I can get this. All right. So the purple line here is without retarder. It's our reference mix. This is normal curve of setting concrete. If we add a retarder, we delay the set from this point to this point. Now the rate of setting is similar. The rate at which the concrete sets after it starts is similar. And you get a lower temperature and you get a bit extra slump life because of this effect. But this is not the primary. The primary reason for a retarder is from here to here, not this, but it's a byproduct of it. So that's what you're doing when you retard concrete, is you're moving the setting point by 1 hour, 2 hours, whatever you need to do. So not only do they move the setting point, but they can actually slow down the rate of setting as well, depending on what you want. Mainly these are used in hot countries and mass concrete, mainly. But it depends on the cement you're using. It depends on the application that you're doing, which type you use. Here's a word of warning. The name is clear, right? Retarder. So if you overdose, if you use more than the recommended dosage, then you're going to have a problem. Now, worst case scenario, the concrete may not set for 3, 4, 5 days. Sometimes the concrete, if it's exposed to the elements, will form a crust on the top. So it feels spongy, but when you break through that crust, it's still soft underneath. And in this case, you have to remove it and reapply it. So for retarders, be very careful with dosing. I've had personal experience, which I'll show you some pictures later, where the retarder was overdosed and the concrete had a major setting issue. So we're not trying to scare anybody, but you should be aware that retarders, if they're overdosed significantly, can have a major problem. So where do you use retarders? Extension of workability by default, high temperatures and mass construction. These are the areas where you normally use retarders. Now, on the other hand, maybe you're in a precast operation, or you have a site that's cold certain time of the year and you want to accelerate the setting or the strength, then you use an accelerator. Retarders retard the set, accelerators accelerate the setting, or the hardening. There are two types of accelerator, which we'll cover in a minute. And they are primarily driving the hydration process at a faster rate. One of them is anyway. And that's this from the Ghana range, it's the Rapid 601. Let's see how that works. There's two types, as I said. Let me show you. Okay, so in our going back to our graph, we have the normal concrete, the control reference. Now here we're moving the point from here, yeah, that's it. So we're losing workability because the setting time is changing. Okay. This is a set accelerator. So we move the setting point to earlier. So we don't have the workability retention, it's gone. It drops much faster than in normal concrete. Okay, but the rate of hydration again is similar. This is a set accelerator. Now, if we go to a strength accelerator is different, hardening accelerator. The setting point is the same, but the rate of strength development is much faster than a normal concrete. Okay, so this is the one that mainly MC focus on. Sorry, I'm getting distracted. This is the one that MC Fast Kick and MC Centrament Rapid. They have good experience and practical application of these types of hardening accelerators. So the reason we focus on this particular type is because often workers want to still be able to use the concrete for an hour. So they don't want the setting point to change too much, but they want rapid early strength. So this is why this type of admixture is much more convenient for a precast type operation, where we can really maximize the strength development. So reasons to use an accelerator: to improve the early strength during low temperature, or if you really want to go extreme, shotcrete applications. Now, shotcrete is a special accelerator. It's not the same technology, it's different. And here you're setting the concrete within 5 to 6 seconds from the point of application. So that's really special, but it's very useful for tunneling and things like that. Normally they're used with accelerators, with superplasticizers. You should do trials to check to maximize the strength. They're used in situations where, for example, if you're doing a building and you want to cast your columns, but you want to speed up the process of building, then you can accelerate the columns to get the strength to support the next layer, as an example. But primarily they're used in cold environments or to boost the strength in a precast application. So there's not much risk from accelerating. You can, this will sound a bit ironic, but if you use a high dose of accelerator, you can actually retard the concrete, so you get the opposite effect. But normally, if you're within the 2% maximum dosage, it should be okay. Not, as the last part of that slide says, not a substitute for good concrete practice. Some people try and, let's speak very openly, some people try and reduce cement and accelerate the strength to hide the fact they've saved cement. This is not the way to work. This is not good concrete practice. We should always stick to the best concrete practice and the right design for the right application, with or without accelerator. All right. Now, air-entrainers. I took it out and then I put it back in because it's quite an interesting topic. Now, maybe not in Africa or where I am in the Middle East or Asia, but in Europe, this is very, very, very popular. And there are applications that you may come across even, you know, in Africa where air-entrainers are needed. So here we're talking about entraining or purposely introducing air into the cement phase of a concrete mix. Now they're very specifically fixed size, between 0.02 and 0.02 and 0.3 millimeter. We're not talking about the air that you see popping out of the mix when you finish mixing your mix, or the entrapped air. We're not talking about that. This is specifically shaped, as you see in the picture, specifically shaped bubbles that are introduced into the concrete for a very specific reason. There are a few reasons why you might want to do that. The main reason is for a freeze thaw. As concrete freezes, the water inside expands and it eventually causes degradation of the concrete. But in our application, it can be used in a few other ways. So for example, if you have poor fines, your sand is not very good, you can often use an air entrainer to help improve the rheology of the mix. It will, very low dose, will introduce a little bit of air and soften up the mix, and it will be nice like that. It can improve pumping due to the reduced friction that you get along the line. It can reduce bleeding if you have a problem with bleeding, and it can be used even for cost reduction because it occupies a percentage, normally around 5% of the mix volume. So you can use it in various ways to improve the rheology of your mix. However, for every 1% air that you introduce into your concrete, by a rule of thumb, you lose around 4% of your strength. So if you're going to design a concrete that has 5% air, you could lose up to 20% of your strength. So you have to account for that in your mix design calculation, because you'll need more cement to meet the same strength. So it has advantages, but it has disadvantages also. As you might imagine, if you overdose these type of products, you get a lot of air and the mix is not very sustainable at all. It's too weak and it's not going to hold together very well. So again, we need to be careful, but these are very useful in our product portfolio. You can use them for various reasons: concrete with low unit weight, concrete with better workability, as we said, poor grading, and freeze thaw. Some use them for lightweight concrete on the roof of a building to offer insulation to protect the upper layers from the heat, but also to reduce the load on the building by making the top layer very lightweight. So here you see, for example, a foam concrete that's absolutely full of bubbles. There's no aggregate, it's just cement phase, sand and bubbles. And you can see the concrete there is floating quite happily below 1000 kg. Of course it will float and be very good for insulated blocks, cavity filling, and things like that, lightweight panels. So if you have a manufacturer of these types of materials in your country, then this is something that's very interesting. We'll just touch on two more. Integral waterproofing. This is becoming more and more and more common. In the area of the world where I am, in Dubai and the Middle East, the specifications have moved from membranes to integral concrete waterproofing. It's not 100%, but it's much more than it used to be. And this is becoming very common and very easy to use. So we'll just cover it briefly. So if you have a nice solid looking structure like this one here, it looks solid, but actually throughout the concrete there are capillaries. Now that's where water has evaporated and left a capillary running through the concrete, and that allows things to pass through the concrete ultimately. So we want to try and reduce that to the minimum that we can. Now in the admixture world, there's two ways to reduce them. One is to block them with what we used to be called, well, it's still called a pore blocker. And the other way is the new generation of crystalline admixtures. These are the crystalline admixtures that block the pores completely. Now, how do they work? The pore blocker, the old technology, is, as it says, just forms a waxy plug in the capillary and blocks the water. Now, the problem with that is over time it breaks down, many years, of course, and it cannot resist high pressure. So if you have a situation where the water table is high and you're in a basement, it struggles to cope with high water pressure. The crystalline type, the new type, well, there's many reasons why they're good, but let me talk you through the pictures. So here you have a capillary full of water. Now, if you introduce the crystalline materials, which are chemicals and then silica sand, the crystals form in the channel and eventually keep growing and fill the channel till there's no more water. It uses up all the water and then blocks the capillary. Okay, now the advantage of that is that when the water comes, if any water is present again, if there's another leak somewhere, the crystals will regrow. So this is where you hear the term self-healing concrete. Normally to 0.4 or 0.5 millimeter crack will self-heal. This is what it's doing. The crystals are forming and filling the crack. And this is because of the presence of calcium hydroxide. If it dries out like that last picture, the reaction stops. No more crystals will grow, but they just stay there. If then water comes back in, the crystals will continue to grow until there's no more material available and the channel is full. And then there's no more water, so it stops again. So it's very interesting technology because it can stand very, very high pressures. In fact, we're seeing specifications now that demand, the standard test for this is 5 bar for 72 hours. We're seeing demand for product that can resist 16 bar pressure, which is huge. So the demand on this type of product is growing a lot, and this is the MC range that we have. The pore blocker type is the Hydro 1, and then we have crystalline 3 types, the C, the CL, and the CP10. Now, integral waterproofing admixtures, by their nature, do have a negative impact on the strength. So if you're designing a mix that you want to make waterproof, you need to allow for the strength to drop a little bit. Normally what we do, what we recommend, is that you use it in combination with a superplasticizer to reduce the water cement ratio, and then the strength will be higher. So it balances out. So we recommend always use the Centromet proof range with a superplasticizer. And I think that's true for all of these type of products. Okay. Final one, an interesting one, because the technology is different. Semi-dry. Semi-dry concrete. So we're talking here about roof tiles, we're talking about blocks, dry blocks. This is very different to normal concrete. As you can see in the picture, the concrete is dry. It's not vibrated into a mold like we do with normal concrete. It's pressed under huge pressure. And although the products are still called plasticizers, chemically it's a very different type of product. The reason for that is they have to fill the molds easily. So the material must move easily without being sticky, must be compactable, and then must release from the molds when the mold is pulled away. So there's quite a technical requirement on this type of product. So here we talk about compaction aids or filling aids rather than plasticizing. We're not looking for high slump. We're looking for the ability to compact into a nice dense block and then easily release. Now for Ghana and for other countries, we have a nice range for this. The BWA 16 is the old one. It's still very usable, very popular. But we have the new Hydrotech 800 and Hydrotech 863, which are very, very good at giving a nice dry but easily usable concrete. So it's a different type of admixture, but still, as an admixture should, it adds value to the end user. All right, so that's a very fast run through some of the product types and what they do. What I want to do now is just share with you a little bit about quality control and dosing. Because as I said at the start, often admixtures are blamed. And if you work for a ready-mix company or a precast company, maybe you've done that as well. I have done that. I used to work for ready-mix and I've done it, so I know. It's the admixture's fault when something goes wrong. But admixtures are produced in very, very controlled conditions, as I said earlier. And you can see here that there are many, many lists. This is just the standard from the EN, that the many, many tests that admixtures have to go through as part of the quality control process. Also, companies like MC keep retained samples for up to 3 years. So if ever there's a problem, we can go back and test the original sample. It's fair to say, in my experience of nearly 40 years, sadly, that most of the problems that we see from RMC, from precast to projects, whatever it may be, are not a direct causally by the admixtures. Can be dosing, as we'll come to in a minute, can be incompatibility, can be changing cement, can be many reasons. And admixture companies work hard to support their customers in finding the reason why things haven't gone as planned. But often it's not, the root cause is not the admixture. It can happen. I don't say admixture companies are perfect, they're not. But very rarely is it the direct consequence of the admixture itself. So there you go. Normally some external factor has influenced the product itself. That can be many things, storage on site, many other things, which we won't go into now. But just to appreciate that the admixture companies, all of them, and there are many of them around the world, go through a very controlled process to produce their admixtures. Some of our admixture plants around the world look more like industrial factories. So we can be sure that the quality is good. So what does that mean? If we, as MC, tell you the product quality is good, but you have a problem, we would always come back and say, well, did you do trials? Did we do trials? To know the right dosage of any product, we should do trial mixes. That means, as the process is laid out there, do a blank, do a reference mix without any admixture. Use water to get the slump and check the setting time. Then, new batch of concrete using the admixture at the recommended dosage from the manufacturer to see the effect. Here's where many people don't do. Run additional trials at higher and lower dosages to see the effect. So if the recommended dosage of superplasticizer is 1%, run a trial at 1.2 or 1.5 and 0.5 to see what margin you have to play with. It takes an hour in the lab, but it's really worth exploring what the admixture can do. And then, of course, you make your samples and you measure the strength, setting times, air content, etc. Slump retention, of course. Then you should look at the results and adjust. Can you reduce the dosage a little bit? Do you need to increase the dosage? My experience, and I lived in Ghana for 1 year, some as you know, is that everything seems to be 1%. Why? I have countries around the world now that I look after where the normal admixture dosage is 2.5%. And that is because they get the best performance at that high dosage. The cost is offset by the cement saving, so it's not a problem for the cement or the cost. It's just you finding the best dosage to give you the best concrete. And that's this process that you're seeing now. Word of warning. Concrete test results, and it's a question a lot of people ask. Why is the lab results different from the plant? And there are many reasons why that's the case. But generally speaking, in the lab, your results are not as good as you get on the plant. Now, why is that the case? There are equipment differences. In In a lab, you're using a very small scale mixer, whereas a concrete plant lab mixer is 1 cubic meter, 2 cubic meter, up to 3 cubic meter. Much more powerful, much more efficient. So you get better performance from your admixtures. You're of course mixing more concrete, so that has an effect of its own, the volume that you're mixing. Temperature has an effect. Humidity has an effect. A lab is controlled, right? It's fixed. No, it should be fixed temperature and humidity. Water cement ratio, in the lab, we measure it to the drop. Do we do that in the plant? No, it's plus minus. So there are many reasons why a lab trial will not be exactly the same as a plant. So plant trials are the next step. We do the lab trial, we get the performance where we want it to be, we confirm it and optimize it in the plant. That's the next stage to get it right. Okay, last but not least, and the favorite. Where should we dose our admixtures? Plasticizers, as we said, should be between 0.5 and 1.5, no more. The problem is the sugar in the lignosulfonate. There are various grades of lignosulfonate. The highly refined ones don't have any sugar. The cheaper ones have a lot of sugar. So they will retard a lot. So you won't know as a concrete producer, for example, which grade of lignosulfonate is being used by your admixture supplier. And they won't tell you. It's confidential information. But you should be aware that if we use a plasticizer, a lignosulfonate, for example, at a high dose, above 1.5, let's say, there is a risk of retardation. Okay. Now, again, I say again, you should be confirmed by trial mixes before we go to start production. Superplasticizers, naphthalene based, generally speaking, don't have so much problem with retardation. It can happen, but it's not so prevalent. And PCEs, they don't really have a retardation issue themselves. It's more of because we can tailor make a PCE basically for however we want it to perform. So you can do 2% is up to 2%, up to 3% is okay also. It depends on what the application is and what you're doing. Here's an example of what can happen, as I said to you, when you overdose. In this case, it was a retarder. This is a job that I did in Kuwait. Fortunately, it wasn't supplied by me, and I'm saying that very truthfully. You can see on the picture that the concrete is drying out in certain parts, and it's dried out here but not set here. And what happened was the producer of this concrete, who was supporting us on this pour because it was quite big, overdosed 2 batches, 2 loads, and this concrete here didn't set. So you can see it's very, very poor quality. As it started to evaporate, the wind, and it wasn't protected very well, then just areas started to dry out, and we had this crusting effect where you could break through that and the concrete was still liquid underneath. So we do need to be careful when you're using superplasticizers, depending on which type, and retarders, that we don't have this type of issue. Retarders, generally much lower dosage, up to 1%, but depends on the type. And this is the one you need to be very careful with. Accelerators can be, now the dosage of accelerators is different depending on the type of accelerator. It can be up to 30 liters per meter. So very high dosage, but depends on the application and the type that you're doing. Again, the chances of overdosing that is very small because it's already a big volume. So the risk is less with accelerators. Retarders is the one where you need to be really careful. And air-entrainers, again, very low dosage because you're only putting 5% air into the concrete. So it's important to stick to that. Here's a word of warning, a word of advice. These guidelines that are on all the TDSs, all the product data sheets, They are the range that the manufacturer, MC, knows the product will work. So as long as you stay, as we, for example, between up to 2% for the PCE, for the power flow, for example, then the product will work. We know it will work. That doesn't mean you can't go higher or lower, but it's at your risk, and we should always do trials. It depends on what you want to do. And some, as I said, around the world, some countries, they operate outside of the bounds of what we would say is normal, 2%, 1%, and very successfully. Just they have to do trial mixes, prove it works, make their system work, and everything's good. But you need to do trial mixes to confirm that that's the case in your particular situation if you want to do that. Just to say, when you're doing your mix design, for example, here, second point here, that the cement content, so if it says 1% weight of cement, that normally includes the binder. It includes fly ash or slag, for example. So it's total cementitious, not only the cement, because then you can end up underdosing. Very important point. So make sure that when you're dosing admixtures, you do it on total binder or total cementitious. Okay. Just also be aware that as we go through the year, temperatures change, and you may need to adjust your dosage. You may need to have a different admixture reality. But generally speaking, you may need to adjust your dosage to give the same performance at a different time of the year. Some countries have a winter version and a summer version that purposely have controlled differences in setting. And they know come September or October, right, I change to winter. And then in January or March or something like that, they switch back to the summer. This can be done. This is a solution that we've done many times. And, you know, depends on, again, what you want to do as a customer. The last one is to say compatibility. Be careful when you're using a cement for a pour. If you're generally, it's best to stick with that cement rather than change because it's cheaper halfway through the pour, because there are issues of compatibility where you can get a lot of micro air bubbles coming out with the PCEs because it's not compatible with that cement. We fine tune those PCEs to work with certain cements very well. And if that cement changes, then of course the performance of the admixture will change. So we need to be sure that we can make sure the system is as stable as we can do it through the project to ensure everybody is successful. What are the effects of overdosing or underdosing? Delayed set. We gave the warning before, delayed set. For retarders specifically, but can be type G superplasticizers, retarding superplasticizers. They can take 2 days, 3 days to set, which often is a headache for everybody. And, you know, the clients can insist that the concrete is removed and replaced because they have no confidence in the strength. If the concrete is left, it should be cored and checked properly to make sure it's suitable. But this is the major issue with the setting and the strength development. Of course, if you overdose a plasticizer, you're going to get very fluid concrete, and to the point where it can be segregating. So again, be careful if the dosage is 1%, as it tends to be. If you're going to go higher than that, if you decide I want to use 1.2 to save some cement, just adjust the water cement ratio to make sure the mix is not going to bleed and have problems, as we say in the last one. And again, overdosing, the rheology, the cohesion of the mix can be destroyed if you have too much plasticizer. And actually, sometimes you can even see on the surface with the latest PCEs that they're almost like a glossy effect, a glassy effect. And you can see there's too much plasticizer in there and it's coming out. So be careful with overdose of those materials. Final thoughts. Admixtures are your friend. They're there to help. They're there to improve the quality. They're there to improve the performance. They're there to make people's life easier on site. Admixtures can help make concrete more environmentally friendly. We use to make concrete more environmentally friendly, not cement. Cement is a different topic on grinding aids, but for the concrete, we can reduce the amount of cement and make less CO2 per cubic meter, make it more environmentally friendly. Admixtures do save cost, 100%, no doubt, when used correctly, but they have to be used correctly. So take your time, talk to MC, use them properly, and next time we'll go into a bit deeper on admixture usage effect of strength, and most interestingly, of course, for most people, the effect on cost optimization. So